So I just hounded you with this whole concept of oxymercuration reduction and alkoxymercuration reduction. And I said, folks, listen, it's just a fancier way to make an alcohol group. That's really all that it is, or an ether group, depending on which one you use. But the difference here is that it prevents rearrangement. That is the whole point of why we would use it at this case. Mercury is an awful, nasty compound that we want to stay away from. However, sometimes we've got to use it. And in this example, what you're going to see is 4 different compounds that have been made. And they want to know, how could you make it? How could you make these? What kind of alkene would you use, and what type of reagents would you use in order to get to this point? These are the synthesis reactions that I told you that people just can't stand. All right, well, honestly, they get a little easier and easier as we go. And the reason is because you will have more and more choices on doing what you want to do. Okay, so here is the very first one, A. And the question says, you've got to make this. What reagents and alkenes would you use in order to get to this point? All right, so looks like this is the group that we're adding on, right? It told me I needed to start with an alkene. So there's the double bond in place somewhere. This group has went on it probably at some point in time. I could have chose the other side if I wanted to, but this side would have been a little easier. And this piece is attached to a carbon. It's a very good sign that that carbon was a double bonded carbon. All right, so I need to add something to an alkene in order to get that product. That is how this is going to work out. Okay, well, let's redraw the product. There we go. And this time, I know that this is the piece that we've added on. So I'm going to erase it. And I'm going to erase the bond that goes to it. That also lets me know that that carbon probably was part of a double bond. I could have drawn it up or down. It doesn't really matter. It's the same whichever way I go because there's no difference in the sides of the molecule. So there is an alkene, at least in the very beginning now. And I need to know, what do I need to add to this in order to get this piece? There's a couple of options for you at this moment. Some of you might say, well, look, we've made an ether here. This CH3, CH2O could have been an OH with a little bit of acid. And this would have been choice number 1. And if you told me that, guess what? Ding, 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 you're right. Good job for you. Because in this setup, my double bond would break. Hydrogen would play with other hydrogens. It doesn't really matter where it goes at this point. And the OCH2CH3 would go onto that molecule without a problem. All right, so there's number 1. But folks, that's not your only choice. That's not your only choice. Now, the directions said, how could the following be synthesized from an alkene? That's all that it told me. But there is another possibility that we could have used at this point. And I know that this is a little bit more complicated. All right, there's number 1, there's number 2. I need to get maybe another way to get that OCH2CH3 onto the molecule. How can I do it? Well, I now know there's a such thing called alkoxymercuration. So this mercury compound with this O2CCF3 parentheses 2 blah 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 with the alcohol group. Well, in this case, it's CH3CH2OH, that's ethanol, with a little bit of sodium borohydride. That would do it as well. There's no difference in the products. I would end up with the same thing. That would still break my double bond. The hydrogen would still go on to one, and the OCH2CH3 would still go on to the other. Folks, it gives me the same product, either route 1 or route 2, and both of these answers would be correct. Whichever one you wanted to give me. because it didn't give you any restrictions on what to use. It just said start with an alkene, and I did. All right, so there's part A. Part B. Part B, it gives me a ring, a 6-membered ring. There we go. And then here we have a CH3 group, and we also have an OH group right there. So we need to make it. Okay, so how do I do this? Well, I'm going to come down here, just like before, and I'm going to draw this OH group and this CH3 group. There we go. There's where we start. So I know that we have probably added on this OH group. I mean, out of the things that we've talked about, that's really the only thing that we could add on. Halogens and OHs and ethers at this point. That's about it. Okay, so that OH group had to be added onto this molecule. So therefore, what do I start with alkene-wise? I know that this is a target carbon right there. I know that that's a target carbon. And this carbon probably has to have a double bond. Now, it doesn't matter if I draw it up or down. It's the same on both sides. It doesn't matter. Who cares? Do whatever you want to do. Do whatever it feels good. But now I've got to figure out what kind of reagents would work here in order to give me this. How can I add on the OH group? All right, well, there's two choices yet again, isn't there? Yes, there is. Yes, nod your head up and down. Yes, there's two choices. The first choice that you could do is add water and a little bit of acid. What would happen here is that the double bond would break. H plays with other H's, so therefore H would go here, and then the OH group from the water would go there. And folks, that's what you got up here at the top. So there's one way that we could have made that alcohol. All right, so that's good news. Now, number 2, there is a second way. That second way is going to use a little bit of mercury and water, right? That was the last set of reactions that we talked about. No big deal. It gives you the same stuff, whatever. HgOAC2 and a little bit of water here, and maybe some THF. And then number 2, NaBH4. That was the setup. That was the set of reagents that we used when we talked about how to break this double bond, and mercury goes on first, and then the OH group goes on where it should go on to every single time, and then the NHBH4, that sodium borohydride, takes one of its hydrogens and replaces the mercury with it. Folks, either one of these would be okay. They give you the same answer. They give you the same product. Again, the difference is this set down here at the very bottom, that is going to prevent rearrangement. My water and acid rearranges, if it could, and my alcohol and acid rearranges, if it could. But we didn't have to worry about that in A or B. They were symmetrical. They were the same on both sides. So that carbocation was not going to move on me at all, period. All right, C. C is going to give me CH3, and then CH, and then CH2, and then CH3, and then down here below, we have an O, CH2, CH3. So they want to know, how do I make it? I'm going to do what I've done before. All right, so we'll write down what they give me. The directions tell me it had to be a double bond. An alkene had to be involved. So it looks like maybe they've added on this OCH2CH3 group. All right, that's fine. I'm going to erase that group because we need to add that group on, and I'll erase the bond that goes up to it. And now I've got two choices here. I could put my double bond to the left, or I could put my double bond to the right. But I need to be able to pick out the best possible scenario. How can I get that product and ensure that that product is formed? Now, the issue here is that if I put the double bond to the right-hand side, look at this. I would have to erase a hydrogen, wouldn't I? And the incoming groups would look at these two carbons and say, well, you know, I really don't care. I don't really care where I go because H goes on one side and H goes on the other. It's a tie. So when this hydrogen comes into play, it can do whatever it wants to do, and then the other group will go on the other side. Well, it just so happened that this is a symmetrical molecule, and that will work for you. All right, it will work for you. It will give you what you want every single time that it happens. You will end up with this product. However, I want you to keep in mind that these possibilities are going to exist, and you need to ensure that the product is going to do what you want it to do. And if I choose to put the double bond to the left and get rid of one of those hydrogens, okay, this is going to form a carbocation that is primary when that double bond breaks. And that group is ensuring that it's going to go to that second spot. I mean, there is no rhyme or reason about it. I do not get a mixture of whatever I get a mix of. It just so happened the other route would have done this too. But this would have been the better route almost every single time. And I just kind of wanted to mention that here. So if I put the double bond to the left, I need to add something that will break the double bond and put H on one side to play with other hydrogens and the OCH2CH3 on the other carbon. How do I do that? Well, option number one is to use an alcohol, CH3, CH2OH, because that's the group that you want to put on with a little bit of acid. The double bond breaks. H plays with other H's. I get a CH3 on the end, like it should be. And then on that second carbon, I have the OCH2CH3, and that is the group that goes on here. This is the ethoxy group. All right, so there's one way to do it. Another way to do it, though, is using the alkoxy mercuration. So this is the big long arrow. A second route. It doesn't rearrange, but that's something I'm not really concerned with here. I mean, whatever. It's the symmetrical molecule, the same on both sides. But if rearrangement was a problem, this would have been a better option for me. So I need that mercury. Because I'm using an alcohol, this compound really changes on me a little bit. OCCF3, 2. And then I bring in the alcohol that I want to use, and in this case it's ethanol, CH3CH2OH. That will give me the piece that I need. And then in the final round, it's sodium borohydride, NaBH4. All right, so there's the answer to number C. Either one of these routes are okay. It didn't tell me to pick one or the other. It just said start with an alkene. All right, so there we go. All right, so for D, this is the last one. CH3, carbon, CH3, and then I have an OCH3, and then here I have a CH2, and then a CH3. So we want to know, how do we make this? What would be the best alkene to use in order to make this compound? All right, well, just like before, here, folks, I'm going to start here. You know what I do. Again, you know my process. Hopefully my process works for you as well. If not, we're in trouble. All right, so there we go. I know that this OCH3 group was probably added on. So that's where I'm going to start. I'm going to erase that OCH3 group. I'm going to erase the bond that was there. And I need to draw a double bond somewhere. Okay, and I need to draw a double bond in a way that will ensure that my OCH3 goes onto that second carbon the way that it is right now. So this is a CH3 group to the left and a CH3 group to the up above. It's really the same. I could choose either one of those. I'm just going to go left-handed to make it simple. And in doing that, I'm also going to have to get rid of a hydrogen to make room for that double bond. And there we go. So there's an alkene. And this will help ensure that when this alkene does break, when that double bond breaks and two sites of attachment open up, one here, one there, well, it helps ensure that the hydrogen does go to that primary. And this forms the carbocation at this spot. Now, will that spot rearrange? No, it's not going to. The reason is because it's tertiary. So once again, rearrangement is something that I don't have to worry with. So I'm going to get two possibilities out of here. There's two ways to make what I want to make because rearrangement is not going to play a factor in anything. All right, so I'm going to erase this back. I'll put my double bond back on there. There is the alkene that would be suitable for me, and I'm going to react it with one of two choices, and either one of these would be okay. I need to break the double bond. I need to add hydrogen to the left and OCH3 to the right. So that means I need methanol with a little bit of acid in order for that to work. There's my H and there's my OCH3 piece. Number two, well, I'm adding OCH3, so this is going to require an alcohol. So that means I need a mercury compound. Which one? Well, the one for the alcohols, and that's this O2, and then CCF3, and then I need to bring the alcohol in that I want to use, that's CH3OH, and then in step number 2, sodium borohydride, NaBH4. Folks, there you go. There's another 2 routes, 2 possibilities, 2 correct answers that you could have given me, and the alkene that would allow this process to happen to give me the product that's up above. All right, so let's do another example. This one says, how could the following be synthesized from 3-methyl-1-butene? Oh, okay, I see what they're doing now. Now they're giving me restrictions. They're saying you have to start with this. You have to start with the 3-methyl-1-butene. You got to be there. And we want to end up with A, and then we want to end up with B. How do we do it? Okay, so let's talk about these differences. I'm going to go back to the screen. I'm going to clear this out. And we're going to start with our first one. 3-methyl-1-butene. All right, so 1-butene. Butene is 4. 1, 2, 3, 4. 1-butene, which means the double bond happens at carbon 1. So there's that. 3-methyl, 1, 2, 3. So I have a methyl group that's here. There's the alkene that I'm starting with. That is 3-methyl-1-butene. And I need to know, what do we use in order to end up with this product? Okay. Well, let's think about it. It looks like what has happened here is the double bond has broken. And if that double bond's broken, well, I need H on one side and OH on the other, right? Yeah. Because that's what we've added here. We've added an OH group. So you're going to look at this and you're going to say, all right, fine. We need to add on an OH group. So one of the ways that we can add OH groups on is water and a little bit of acid. So there you go. Why is that wrong? You're close. You're close. But that is wrong. And here's why. Here's why. If I add acid and water, remember what I told you very, very early on in another video? Acid and water adds on to a double bond. The double bond breaks. There we go. And 2 sides of attachment open up. One here, one there. Hydrogen gets added on first. Hydrogen plays with other hydrogens, and that forces hydrogen to go here, and a carbocation is formed. But what did I tell you to always do? I told you to always double check rearrangement. And in this case, rearrangement is going to happen. Why? Because right now this carbocation is on a secondary carbocation, and one next door to that, this is a tertiary spot, folks. And that tertiary spot is a better location, and we are all about investments to our real estate properties, aren't we? That's right. So I want to move to the next carbon over, because that's a better location. That's what a real estate agent would tell you. So if this carbocation does shift and it goes there, that would be the location of where that OH would go from the water. It doesn't end up with this. This OH group is on that second carbon. It does not move. We cannot allow rearrangement to happen here. Oh, now I see, right? We've talked about these two possibilities that we could use over and over and over. You want acid and water, or do you want the mercury route? And both of these ended up with the same product almost every single time, but not in this case. Not in this case, because water and acid allows for rearrangement, and this would rearrange, and it doesn't give you the product that you're after here. So water and acid, it's wrong. This is not going to work for us, okay? But what will work for us? How else do we get an OH group onto a molecule, but yet ensure that that is the spot that my OH wants to go into? Well, I use the mercury route. That's the whole purpose of it. It prevents rearrangement. All right, so that means HgOAC2, and I need to add in a little bit of water and maybe some THF. And then on the second route, I'll use sodium borohydride. That way the mercury breaks the double bond. The mercury adds on here first. Then that will free up this carbocation that does not move based on the mechanism. That also then means that the OH from the water, that's the spot that it will go to, and that's where it needs to be. Down here in the bottom, we see that's the location that we're after. And then eventually that mercury will be kicked off, and the H from the sodium borohydride will go onto that spot. And it gives us this product that we're after. So this is the only answer that you can give me right now. Now, are there other ways to make this? Of course. Of course. There's tons of different choices. We're just learning them in little bits as we go. And right now, you only know two ways. And one of those ways is not going to work because this rearranges and it's going to give me a different type of alcohol than what I'm after. So the mercury route is the only route that will work at this point in time. Okay, so that's the answer for A. Now let's take a look for B. B says this is what we want. CH3, CH, CH3, CH, CH3, and then AOH that's here. We want to make this. And we want to make that from 3-methyl-1-butene. Okay, so that's the same molecule that we started with in the very beginning. 1, 2, 3, 4. They're giving me limits. This is the only thing I can use. 1-butene is going to be there, and then 3-methyl is going to be here. They're telling me you have to use this. You got to use it. Sorry. No other choice. What could you use in order to make this molecule? Okay, well, if I look at this, it looks like my OH group has been added on. How do we add on OH groups? We know there's water acid, and now we know there's mercury. One of those two routes, the only thing I can choose from. So let's take a look at this process and figure out which one's going to be best. If I use the mercury compound would break the double bond. Two sites of attachment would open up here and here, forcing hydrogen to go here and OH to go there. Now, is that what we want? Is that what we want? Well, let's take a look at this. It doesn't look like a perfect match, but is it? Well, here my OH group is 2 from the end, and here my OH group is 2 from the end. Oh. And then my methyl group, if this is the end that I start numbering from, 1, 2, 3, 4, my methyl group is right there at carbon 3. And if this is the number that I start from, 1, 2, 3, my methyl group is at carbon 3. Folks, these two have the same name. They're just written flipped. That's all that we've done. We just flipped the molecule around. They've tried to trick you. That's what they've done. So if I can get my OH group at that position and prevent rearrangement yet again, then this would allow me to get what I want. So we've got, I don't know why it keeps doing that. So we've got an alkene. Let me erase all of this mess. We've got an alkene. That alkene's going to be there. We prevent rearrangement from happening We don't want it to go forward. Therefore, Hg, OAC, 2, water, THF, NaBH4. And there we go. That prevents the OH from rearranging. That's something that we don't want. And there's our molecule. Okay, so there's 2 more examples. Are there more? And the answer is no. There's not more. Sorry, there's no more. However, I do want to go back and I want to talk about the THF. I told you THF stands for Tetrahydrofuran, and we would look at that structure in a different video, and here's where we'll look at that structure. The structure of THF looks like this. Okay, it's a cyclopentane ring almost, but instead of a carbon at one of the locations, there's an oxygen. I like to call this the cupcake molecule because I think it looks like a cupcake to me. If I take this top piece and there's my icing and there's the rib of the cupcake, and that could be the little cherry on top, that is the cupcake molecule, and that's what I refer to this as. So THF is tetrahydrofuran. They really do like for you to draw THF and get familiar with THF. It's one of those solvents that we use all the time, so they would just like for you to become more familiar with it. You're going to see that this is not the only time that we're going to use THF in a series of reactions, but it's going to come around again, and it's going to come around multiple different times. So now you're a little bit more familiar with the structure of the THF molecule. All right. I also want to go back and I want to take a look at this problem that we just did. I don't know if I made a mistake. I might have done the same question twice. I don't really know. But I'm going to go back and take a look at A. And if you look at A, notice this OH group has been shifted. And I can't remember what we just did. That's how loony I get sometimes and wrapped up in these videos. But 3-methyl-1-butene is 1, 2, 3, and 4. Here is the methyl group. There we go. This double bond has to break, and that double bond breaks, freeing up 2 sites of attachment. I think this is what we just did, but if not, I'm just covering my bases. If the OH group want it to go there, it can't. I cannot use mercury. I have to use water and acid. And water and acid will allow a carbocation to shift to happen, and that allows the OH group to go here. And that is where that question wants it to be. So for A, the answer here is water and acid. That would be appropriate for that molecule production. Okay, the double bond breaks, hydrogen adds on to the left-hand carbon, the carbocation forms on that other one, the carbocation shifts down, and that is where this molecule wants it to be. So water and acid is correct for that one. And I can't really remember what I just did, quite honestly. I'm slipping. Or the other reason is that I've just recorded too many of these videos back to back to back, and it's time for me a break, right? Okay, so there's the problem in 23 for A and B both. All right, so in the next video, we're going to focus on another reaction. That's right. Yay, another reaction. How many? Please make it stop. But we've got a couple of more that we need to talk about. We've got a couple of more that we need to discuss and walk through, because there's going to be a total of about 10 or 12 of these. And we're getting closer. We're getting closer, but we're not quite finished yet. And in the next video, we're going to talk about something called hydroboration.